Welcome to Lyons Township High School AP Physics. Today we got an example involving standing waves. Specifically standing waves on a guitar string, okay? And then a standing wave in a closed pipe, a pipe closed at one end. The pipe will be open at the top and it'll be closed at the bottom, okay? So we'll start with the guitar string, okay? And the example I'm going to do is we're going to pluck that string and I'm going to tune it to 220 hertz, which is an A note in music. My reference, it says A note, third octave. Okay, I'm not a musician, so I hope that means something to most of you. We're going to tune it first, and then I'm going to calculate how much tension has to be in the string to make the frequency of 220 hertz. So I'm going to start with that. So when you pluck a guitar string, this would be a node, and this here would be a node. So you got two nodes, okay, acting, and then you got an antinode in the middle, okay. So what does that look like, okay? Well, you got a node there and a node there, and your string's going to look like that. Half a cycle later, your string will be here. So at any one moment of time, how much of a wave is that? Well, it's either a crest or it's a trough. So at any time, it's half of a wave. So the length of this thing, L, okay, the length of this thing is 1/2 of a wave, okay? Now, it turns out there are other frequencies that will make this thing resonate as well. I'll go into that near the end here. But for now, we're going to deal with that. So the wavelength would be 2L, okay, right now anyway. Now, the length of this thing, by the way, is 65 centimeters, okay? So I'll make a note of that. So L is 65 centimeters. So 2 of that would be 130 centimeters, or the wavelength would be 1.3 meters. So that's your wavelength, okay? How am I going to tune it? Okay, well, I've got a tone generator, okay, and I'm going to set this to 220 hertz. Okay, so hopefully you can hear that in the mic. And right now, the guitar string is not tuned, okay? If I pluck the guitar string next to that, okay, hopefully you can hear that. There's a wobbling, okay? That wobbling that you hear is called beat frequency, okay? Beat frequency means the difference in the frequency between the one tone, which is I know is at 220, and the guitar. So what I'm going to do is I'm going to adjust the tension in the guitar string until the two frequencies match and I don't hear that wobbling anymore. That'll be when the beat frequency is 0. Okay? All right, so here we go. Oh, I think I just about got it. Okay, now one way to check, okay, yeah, I've got it. Right now the guitar is off. I'm going to let it go for a sec, and if I turn my tone generator off, you can hear the guitar string is still vibrating. So now this speaker set the guitar string vibrating, which means they're both at the same frequency at that point. And by the way, that's called resonance. This would be what we would refer to as a forced vibration, and that is matching the natural frequency of this guitar. So this guitar resonates. We call that resonance, okay? All right, so I know my guitar string is now at 220 hertz, okay? What's the tension in the guitar string? Well, there's an equation that involves tension. The velocity of a wave in a string or a spring or a slinky is the square root of the tension force divided by the linear density of the string. That would be kilograms per meter. So if I took a meter of string and weighed it or massed it, how many kilograms would it be? Now it turns out for our guitar string, that is about 0.5 grams per meter, okay, which is going to be 0.0005 kilograms per meter. So now I know this, okay, and by the way, that's not wavelength. A lot of people confuse that with wavelength. This is linear mass density. A little tricky there. Need to find tension. Got to know the velocity of my wave, okay? Well, the velocity of the wave is simply wavelength times frequency. And I've got the wavelength, it's 1.3 meters per wave, okay? And I'll write that down, per wave. And the frequency, I told you it's an A note, that's 220 hertz. So my frequency is 220 waves per second. That's a hertz, okay? So if I multiply those out, V equals lambda, which is 1.3 meters per wave, times the frequency, which is 220 waves per second. The waves cancel out, and you get meters per second. And my velocity of the sound wave, or no, the velocity of the waves in the string are 286 meters per second. So now that I've got the linear density of the string, and I've got the velocity that the waves are traveling in the string, I can now find the tension force in that string. If I square both sides, I get a V squared, multiply by that. You get force of tension equals V squared times, I'll put a little m there for linear mass density. So for us, this would be 286, got to square that, and then times the linear mass density in kilograms per meter, which would be 0.1235, okay? And if you do that, you should get a force of tension of about 40.9 newtons, which is about 10 pounds or so, or maybe 9 pounds. So that's the tension in this guitar string right now, okay? Now, the other question I had for you regarding the guitar string is what other frequencies would cause the string to vibrate, okay? So this would be what we call the fundamental frequency, okay? That would be like F naught, okay, which is 220 hertz. Well, you always are going to have a node at either end, but then you can have as many nodes in the middle as you want. So for instance, you might have the two nodes at the end. This thing still has a length L, but you could also have a node in the middle, okay? So that would be your string at any moment. That would be a half cycle later. So at any moment, how much of a wave do you have? Well, now you have a full wave, right? One crest and one trough at any moment. So the length would be simply 1 times the wavelength. Or the way I'll write this is 2/2 times lambda. You could also have both ends are nodes. You could have two nodes in here, crest, trough, crest. Okay? At any time, in that case, the length is, well, now you have 1.5 waves or 3/2 of a wave, okay? So hopefully you'll see a pattern. L is simply n/2 times the wavelength, n being the number of antinodes you have, the number of these loops that go up and down. You can rearrange this for wavelength. Wavelength would be 2L/n, n again being the number of antinodes or which harmonic you're on. So like they would call this the fundamental frequency or the first harmonic. This would be called the first overtone or second harmonic. This would be the second overtone or third harmonic. Okay, so whatever harmonic you're on, that's just n. Now for frequencies, what's not going to change is the speed of the wave in the guitar string. Okay, if I'm not changing tension and I'm not changing the string itself, then this is not going to change. So as I make the wavelength smaller, as I put more and more waves on the string and make the wavelength smaller, the frequency goes up. So for instance here, if I go from that to that, I have made the wavelength half of what it was, so the frequency would simply be double. And here I've made the wavelength a third of the original, so the frequency would be 3 times the original. So the original one would be 220 hertz, this would be 440 hertz, this would be 660 hertz. So those frequencies would also make the guitar string vibrate, okay? Now, the second part of this is, what if I want that same frequency in an air column? So now I want to go from a guitar string to a column of air, okay? What's the one thing that will be the same for the wave in the guitar string and the standing wave I'm going to make in the air column. So you got three things to choose from. It could be wavelength, it could be frequency, or it could be velocity. Okay, which one do we want to be the same? Well, I want it to be the same tone, which is frequency. So the only thing these two will have in common is they'll have the same frequency of our 220 hertz, okay? Everything else will be different though, okay? So for instance, for sound, we know that sound varies with temperature. And the velocity of sound follows a fairly simple equation. The velocity of sound is 331 plus 0.6 T. T is the temperature of the air in degrees Celsius. In the room right now, the temperature of the air is about 20 degrees Celsius, about 72 degrees Fahrenheit. So if I put a 20 degrees Celsius in there, I get 331 plus 0.6 times 20, that's 12. V of sound is about 343 meters per second in this room. So notice that's different than the velocity of the guitar string. The guitar string had a velocity of 280 something. This is a little faster, okay? Now the other thing too is we're in a closed tube here, okay? So we know we want frequency to be 220 hertz. We want the same tone, okay? So how long should I make the air column? Now, by the way, I'll make a note. The air column will be from the top of this tube to the water. And hopefully that water is showing up on the video. This tube is filled with water, so like right now the water's there. So the length of this air column would be from here to here. And it's closed at the bottom, and the water's in the way. So what would that look like? Well, here's your pipe. Get this out of the way for you. Okay. And it's stopped up at the one end and it's open at the other. So when I put a sound wave near this, the air molecules can move around here, up and down. Whereas down here, they're kind of stuck. The air molecules can't move because there's water in the way. So we call this a tube closed at one end. So if I'm looking at the velocity of the air molecules versus time, let's say, well here there's not going to be any velocity. They're stuck. That's a node. Whereas here, the air molecules can slosh up and down. That would be an antinode. So if you could see a transverse wave in there, it would look something like this. That would be at a moment. This would be at a moment later. Now we're going to have this. It's going to have a length L, the closed tube. How much of a wave is that? Well, we're going from a node to an antinode, from a node to a crest, or an equilibrium point to a crest. Well, that's a quarter of a wave. Okay, so the length of this thing is 1/4 of the wavelength. Now, there are other frequencies which will work. I'll mention that. There's always going to be a node at the closed end. At the open end, there's always going to be an antinode. So, for instance, you could do this. Okay. How much of a wave do you have now? Well, you have a half and a quarter. You have 3/4 of a wave. So L in this case would be 3/4 of a wave. And the pattern's pretty simple. L equals n quarters of a wavelength, but n has to be odd integers, okay? And you can rewrite this as wavelength is 4L over n. Now again, n has to be an odd integer, okay? So we're going to do this example, the first point at which the tube will resonate, okay? Now, we know the frequency, and we know the velocity of the sound wave, so we can immediately find what their wavelength's got to be. Okay, so if I do that, velocity is frequency times wavelength, or wavelength is velocity over frequency. So wavelength is 343 over 220. Oops, sorry about that. And if you divide that out, you get 1.56 meters. Okay, so that's going to be the wavelength of the sound wave. So they're about yay long, okay? And we want to know how long this air column has to be. Well, the air column is going to be 1/4 of that length. So in this case, L is going to be 1/4 of the 1.56, which is 0.39 meters or 39 centimeters. Now, that's almost correct. It turns out that there's a correction factor. The antinode ends up being slightly outside, about there, slightly outside of the tube, okay? we call that a correction factor. That is actually not exact. Depends on which source you look at, maybe which textbook you're looking off of, or which internet site you're looking at. But here's the one I found. The length of the air column will be, the length of the air column that will vibrate, that will have our standing wave in it, will be the one I measure plus 0.4 times the diameter, that's this here, the diameter of the tube, okay? Now I measured the diameter of the tube, and the diameter of the tube is almost exactly 4 centimeters, okay? So this is going to be 4 centimeters, okay? So L, which we want to be 39 centimeters, is equal to L naught. That's what we're going to actually measure. So we're going to actually measure the distance from here to here. That's going to be our L naught. So that's L naught plus 0.4 times 4 is 1.6. So L naught, the actual distance I'm going to measure, would be 37.4 centimeters. So assuming that the air temperature is about 20 degrees Celsius, and assuming that our corrected length is correct, then I'm going to turn this tone generator on to 220 hertz, and I'm going to move this around until I hear it resonate. Hopefully over the mic you'll be able to hear that. When we hear it resonate, I'll measure, and hopefully we're pretty close to 37.4 centimeters. If we're off a little bit, it's probably because of the air temperature. It's not exactly 20 degrees Celsius. I frankly didn't measure it. But we should be close, okay? So I'll get this ready, and you should be able to see that in camera. I'll turn my tone generator on. Okay, got to turn on to 220 hertz. Okay, if you're looking on the camera, there's 220, okay? And then basically what you do is you hold the speaker over this. Now, if you do this in a laboratory setting, oftentimes you'll have a tuning fork, okay? Same thing. And I'll move this pipe up. Oh, it came unplugged. Okay, I'll move the pipe up, and I'll try to put the mic next to it, and you're going to hear it resonate. Okay, so hopefully you can hear that. So there's no resonance. I'll put the mic right up to it. There's resonance, and basically resonance is kind of a loud spot, okay? And we'll check for other ones. Oh, actually that one's much better, so we're going to use that one. Oh, yeah, there we go. Okay, so there's not resonance. There's resonance. It's much louder. Okay, so I'll get it as loud as I can. About there. We'll measure this. And notice that it says, oh my, L is 37.5. So we're within a millimeter of what the measurement's supposed to be. So, hey, guess what? Physics works, okay? So that was an example of two examples of standing waves. The first example, we had a standing wave in a string, okay? And we found the tension in the string required to keep that standing wave. Also, that standing wave had two nodes, one at each end, and an antinode in the middle, okay? So that would be similar to an open pipe, okay? Then we said, okay, if we had the same frequency, or 220 hertz, that's going to make a standing wave in this air column that I created with a closed tube, okay? And we went ahead and found how long would that air column have to be to make that standing wave happen in a standing sound wave happen in a closed tube. So I hope that was helpful, and I hope you enjoyed hearing my lecture, and thank you very much.